colleagues shoes. Thank you. Yeah. Um, so my name is Dmitry Penzar, and I'm a PhD student at Vavilov Institute of General Genetics, and I'm a member of Autosome Team. And thank you for the opportunity to present our solution and for the great competition we all participated. So let's start from the very beginning again. Actually, there are two main families of highly successful approaches that
Sorry,
utilize machine learning.
one sec. Sorry to interrupt you. We see your PowerPoint, but not the actual slides themselves.
Oh, sorry. Okay, 1 second. Uh, yes, 1 second. I think it's yeah, 1 second. Sorry. Mm, I think it's just yes, this one. So now is it okay now?
There we go. You're good. Thank you very much.
Thank you. Okay, so actually, there are two main families of highly successful approaches for machine learning in genome regulatory tasks. The first one is GKM SVM, Delta SVM, our favorite one. It was developed in 2014 and based on support vector machine. This method is not prone to overfitting and provides state-of-the-art solutions for different tasks, from recognition of individual transcription factor binding sites to predicting the effect of single nucleotide substitutions. Unfortunately, this method can be used for datasets with more than 100,000 sequences due to time complexity. So we wasn't able to use it in this competition. The other family of approach is deep learning, and for example, well-known Informer, which was presented by DeepMind in 2021. This method is state-of-the-art um, in genome signal prediction tasks and can be used for large data sets. However, the Informer architecture is designed for large genomic windows and requires enormous amounts of data if trained from scratch. So we had to develop new approach to the problem. From a purely machine learning perspective, deep learning applications in regulatory genomics unfortunately lag behind state-of-the-art solutions in deep learning, in general deep learning, by 3 to 4 years. For example, one of the most famous convolutional neural network architecture, um, AlexNet, was presented in 2012, and it took 3 years to adapt CNNs to nucleotide sequences. Another example is given by attention transformers, which were presented in 2017. Yet Informer was published only 4 years later. So, in searching for the best model for predicting the activity of regulatory region, it's promising to look for the most advanced and up-to-date architectures. We know that nucleotide sequence scoring problem can be formulated in terms of natural language processing and image recognition. In case of natural language processing, we treat the whole sequence as a sentence in natural language. The H nucleotide or k-mer is a distinct word. In computer vision, we use one-hot encoding to transform a sequence into one-dimensional four-channel image. So in our solution, we took the later approach. But we know that according to DeepMind experience, the AlphaFold 2, to master hard to crack problem, you have to use all the knowledge you have about the problem. So before moving on with machine learning, we started with domain knowledge. Uh, First of all, given limited amount of training data, it could be efficient to use models pre-trained on nucleotide sequences and omics data. Unfortunately, the idea goes against the challenge rule. So, what do you know about data? The data is imperfect and noisy. Specifically, the integer values are likely measured with a low precision, as they most probably correspond to the singleton promoter sequences observed only once. The expression value is not direct outcome of the experiment. The underlying procedure estimates the observed frequency of sequences in each bin, and the frequencies are then used to calculate the expression value as a weighted average. Also, from biological perspective, promoter iteration matters, and reverse complementary sequences may have different properties. However, there are some complementary elements or even whole promoters acting in a strand-independent way. So, a proper strategy should allow the model to decide. So how we are going to represent our input data? We use the one-hot representation of promoter sequence. A reverse complementary sequence is considered independently, and the sequence orientation is marked explicitly in the binary reverse channel. The reliability of measured expression, a singleton promoter or not, is also taken into consideration by using a dedicated binary singleton channel. Also from Boyer et al., we know that the expression value uh, follows the normal distribution. So we transform the provided expression into a continuous normal distribution with constant values, variance equal to 0.5 and mean equal to expression plus 0.5 also to account for the discreteness of original experiment distribution. So and we we obtain probabilities of falling into each bin for each sequence and train model to predict these probabilities. Uh, and so we allow for uncertainty in the original expression values estimate. Also, we know that in computer vision, the actual state of the art is efficient net V2. It has increasing performance, relatively small training time, and train model is comparably small and applicable to small data sets with reduced risk of overfitting. Efficient net V2 is a fully convolutional neural network with several sophisticated tricks. And we will repurpose these tricks to decipher regulatory sequences. Let's have a look at the overall NogiNet architecture. The input is passed to the stem block. Actually, it is a usual convolutional block, followed by the sequence of 6 efficient net V2-like blocks, followed by a mapping blocks to transform resulting features into a prediction. In more detail, stem block consists of simple convolution with kernel size 7, followed by batch norm and activation function. Efficient net V2-like block uses the ideas of the original efficient net V2 neural network. First, there is a convolution with kernel size 1 to map input features to increase dimensionality. Next, there is a group convolution. Its results are scaled up using with an excitation block. And features then mapped to the initial number of dimensions using convolution with kernel size 1. After that, we concatenate the input of the block with its output in a paternal manner and pass the result to the block of the same architecture as the stem block. Actually, the squeeze and excitation block was really complicated even in efficient net v2. And we have added more tricks on top. So let's pass to the key idea. And the key idea of this block is to allow the featured channels to communicate with each other and as a result adjust their activations. And actually this can be considered as some form of highly regularized attention mechanism. Mapping block consists of convolution with kernel of size 1, which reduces the number of channels to 18, and global average pooling, which calculates each channel mean. The resulting 18 numbers are interpreted as raw probabilities, and during the training phase, we convert them to the actual probabilities using softmax. During evaluation, we use soft argmax instead. They again map raw probabilities to actual one, but then we multiply them by the corresponding bin number. Thus, we get expression value, actual. But also from multiple studies, we know that not only the architecture matters, but the training scheme. We tried several modern approaches and found one cycle learning rate coupled with Adam W optimizer as suggested by FastAI courses to be the most promising during the leaderboard stage. We selected maximum learning rate for this approach using learning rate range test described in the original paper of Smith et Topin. As a result, we observed so-called superconvergence. This approach halved the number of epochs required to train the neural network and also increased the model performance, actually significantly. To make final predictions for test sequences, we set singleton channel to 0, as we know they are not so noisy as trained data. And perform test time augmentation by averaging model prediction for forward and reverse trend. As final result, we achieved top 1 performance both on public leaderboard and final leaderboard. Also, we tested our approach on public data and found that, again, NogiNet consistently outperformed the existing models. The model source code, training and validation scripts will be available soon at GitHub of our laboratory. Also, you can check other projects of our team at Autosome.org. Subscribe to my Twitter not to miss further announcements. Also, we want to thank Deep Genomics for sponsoring our participation in this conference. Thank you for your attention.
Your talk. Any questions for Dmitry on the project? Yeah.
Hi, Dmitry. It was a fantastic talk. This is Yosuke from MIT. And you mentioned that try to assume the distribution of the observed counter data by modeling the observation as the normal distribution with the observed mean plus 0.5 and the fixed variance. I wonder how did you pick picking the mean of the normal distribution slightly larger than the actual observed value? Any intuition behind that design?
Yeah, thank you for your question. Actually, it's the source of this addition is the same as the correction we use in approximation of binomial distribution by normal distribution. To get more correct probabilities in this approximation, you have to add 0.5. And we tested if it improves our score, and actually it is.
Thank you. This is very insightful. Thank you.
Hello, Dmitry. So my question is, the way you can you hear me?
Yes, sure.
So the way you integrated, I think, tried to inform the model that okay, some training sequences you should not be so sure about this sequence, by adding that additional channel that is singleton. So did you try to modify the loss function in a way that okay, when you get integer expression values, maybe do not penalize the loss more for them, but for floating value points you penalize the loss more?
Yes, yeah, it's a really good question. Actually, we tried some approaches like that. We haven't tried, I think, penalizing differently integer losses, but we tried several schemes to penalize some bins differently, some values differently. Also, we tried um, to use as other team losses which not penalize model for high errors like Huber loss. And actually it improves sometimes for some of model we have tested, it improves the performance, but in the final model it changes nothing.
Thank you. I think it was a really actually I think cool way to handle this noise in the data.
I'm gonna read a question online. This is from Michele Tinti. Thanks, great presentation. How easy would it be to transfer learning with your code?
Oh, actually it's a really good question, as we have some task like the challenge one, and we are going to try it, but with our code, actually I don't think it would be really hard, as we tried to we tried to keep it as simple as is possible. And actually now I'm trying this architecture for 3 projects, I think, and it's okay. So I think that transfer learning will be okay too.
Any other question? Actually, I have a question. So, I mean, you really fine-tuned your model to the type of noisy data that was shown, right, in the challenge, and to the way the measurements were done, etc. But you also show that it beats, I think, on your last slide. It also beats state of the art for other types of data. What was the data? Was this human data? And so, how do you think that this was possible? That the fact that you trained your model on very specific yeast data, taken in a very specific way, did transfer well to another data set? Actually, I don't know what data set you use, so if you could clarify this.
Yeah, actually, it is the data sets from the organizers of these competitions. They in the very beginning of their talk, they presented 2 papers, and actually this is data from their papers, and we compared with their models. So actually, it is mostly the same task.
So it would be interesting to see precisely in the context of the transfer, right? Like how well we did fare with a data set that was taken differently, right? Yeah.
Yeah, I see. No, we have some preliminary results only that it works pretty well on some tasks. We can say that it will outperform any model you can design, but actually it works better than models designed by my students during the last year. So I think it's a really promising one.
Very good.